Voting is a very important mechanism to understand interactions within a crowd or a network of people. It is an important mechanism to reach a consensus, a binding resolution among a group of individuals out of conflicting configuration of opinions. It is clearly used in many scenarios. In Wikipedia, it is rarely actually explicitly used, as we mentioned, but still we can view extension of the basic voting model as an underlying model of how people react to rough consensus formation there. It is explicitly used in many political systems. Some variant of that is used in jury process. Some of that is used in talent show, and the list can go on. Now, compared to some of the other consensus formation we have already seen, voting is different. It is different from presenting a rank order list for each person to individually evaluate, as in Netflix situation. It is different from using pricing as a way to coordinate people's actions. For example, ad-based auction by Google or congestion control in the internet that we'll see later. It is also different from ranking objects. For example, ranking web pages through PageRank in Google, or ranking products based on aggregation of rating on Amazon. Now, voting is so important that we will go through a tiny tip of this big iceberg in the next 30 minutes or so. And later in lecture 20, we'll also talk about fairness systematically. Voting and fairness theory are the two pillars in the so-called social choice theory that's extensively studied in economics, in politics, in philosophy, and so on. And some of our study will be based on very famous results on the impossibilities of axiomatic systems. But first, let's start with something very intuitive, something that we must have all encountered. It's a simple, basic voting system. There are a lot of variants that one can imagine, but this is a very good starting point, where we have the following input to the system. It is a collection of voting inputs called preference profiles for each voter. And let's say there are n voters. They can rank order m candidates. Okay. The candidates could be real people running for election, or they could be just different choices, options that one need to choose from. So got n voters and m candidates. Each voter would rank these m candidates. So you got a rank order list per person, and you got another one for another voter. The collection of all these lists is called a preference profile. The output to the voting system is a single list called the voting outcome. So they go through this voting system, and then out comes one single list. We are going to require that these lists be complete, meaning that all m candidates need to show up in the list for both each of the inputs and also the output list. In many practical cases, that doesn't have to be. For example, in the rough consensus formation process in Wikipedia, a lot of times the committee members or the editors may not have a complete list. They may say, well, there are 3 choices, and I just want to make sure choice A is higher than choice B. I don't care where choice C might be, whether it's right here or right below there. And in certain voting systems, you have so many candidates that it's impossible to ask people to completely rank them. You just say, tell me who's the number 1 you really want, and then I'll work with that information. So clearly, incomplete input will make the theory richer, but we will not have time to cover that. We also, for the sake of logical consistency, require that each of the inputs and the output list must be transitive. Later, in about 2 lectures time, we'll also look at transitive property in a graph. That's very different from this one. Okay, it's unrelated. This transitive property says that if you rank A to be better than B, A, B are 2 out of the M candidates, and we write that as A bigger than B, and following the same notation, if you also think that B is better than C, then these 2 statements logically must imply A is ranked higher than C in your list. This just to ensure logical self-consistency. Okay, otherwise, you already run into a cyclic situation. If A is better than B, B is better than C, and C is better than A, then this is a self-inconsistent set of input or output. So we say that if A is better than B, B is better than C, it must imply A is better than C. All right, having said what are the inputs and the output of a voting system, you have to realize that any voting system tries to compress information. There will be a loss of information. Okay, otherwise, it will be too good to be true. You start with n list and you end up with 1 list. Of course, this 1 list cannot be reverse engineered to give you the n list. Something must be lost in the process. The question is, can we still maintain something useful? Well, the most commonly encountered voting system is perhaps called plurality or majority voting. Okay. It simply says the following. I'm going to count the number of voters who put a candidate J in the first position. Okay, look at all the lists and say, how many put candidate J in the first position? Say 10 out of 20 voters. Okay. For J, and then what about K? What about the other candidates? And then I simply pick the number 1 candidate in the output list as the one with the highest number of voters to put it on the first position. Then I say the second position, that's the first position, the second position in the output list would be the one with the second highest number of voters to put it on the top of their list. Okay, this is assuming there's no ties. Otherwise, you have to think of some way to break the tie. And this is the majority voting that we encounter in many situations. There is also the mirror image of that called Kameny voting system, which says that we'll count how many least liked vote a candidate receives. Okay, instead of looking at how many people put you on the top, I look at how many people put you on the bottom. For example, 3 out of 20 voters put candidate J at the bottom of their list. Then I'll rank order in the descending, ascending order of the number of people who put you at the bottom of their list. Okay, that will be so-called Kameny rule. Either way, this is a special case of plurality voting. It sounds pretty intuitive, but as we'll see that it can be problematic and lead to counterintuitive results. A second clause is called positional voting. In fact, it is a generalization of plurality voting. Positional voting in general says that if you give me a list of candidates, okay, let's say Alice and Chris and Bob, and then I will assign a certain score to each candidate for this list based on the position. For example, the score could be, if you have a list on the top, I give you a score of 1, and then everybody else get a score of 0. And then I tally the score received by each candidate across all the votes. For example, another vote could be CBA, and another vote could be ABC. Then I see that A received a total score of 2. Okay, so 1 plus 1 is 2. C receives a score of 1, and B receives a score of 0. And therefore, A is ranked the best, followed by C, followed by B. As you can see, this actually realized the special case of a plurality of majority voting. But in general, the positional voting system doesn't have to assign 1 to the top and 0 to the rest. In fact, one other way is to say I'll assign m minus 1 points to the top and n minus 2 points to the second one. And then eventually I'll get to the bottom of the list, then I'll assign a score of 0. Why don't we assign n minus 1 all the way down to 1? Well, because since we require each input list to be complete, so all the candidates will show up in each list somewhere. So the fact that it shows up at the bottom of the list really does not carry any information. Maybe this voter really hates this candidate, but still it will be somewhere, say the bottom of the list. So the bottom we say you are there possibly just because it needs to be a complete list. So I will give you a score of 0, and therefore the top one receives a score of n minus 1. So in this case, A would get a score of 2, C gets a score of 1, B gets a score of 0 for this input list. Then I add up the score you get from all the input list, and then that gives me a number. And then once I get m numbers, I can rank order the m candidates. This is what's called border count. Border is a French mathematician that started the rigorous study of voting system. Now, you may wonder, why is voting sometimes difficult? Perhaps that's because we're trying to compare too many candidates. Okay? When n equals 3 or more, it becomes very difficult. Why? Because if n were just 2, then it's easy. If there are only 2 candidates, Alice and Bob, okay, then for whatever method you use, we can give an exact comparison between the two for each input. Okay? Then I can use a single scalar to represent that comparison. Then I got n scalars from n voters, and comparing scalars is fine. In other words, it boils down to the following. On a real line, comparing 2 points is always easy because there is a full order. Whereas on a 2D or higher dimensional plane, comparing 2 points is difficult. Like, can you say this point is bigger than this point or not? Well, it's bigger in one dimension and smaller on the other dimension. So if there are only 2 candidates, comparison becomes a scalar operation, and therefore ranking becomes easy. But since pairwise comparison is easy, let's just only do pairwise comparison. Okay, we just look at all the possible pairwise comparisons. For example, if there are 3 candidates, I'll look at A-B comparison, A-C comparison, and B-C comparison, all 3 possible pairs. Okay. And if pairwise comparison between A, B says A is better than B, we write it down. And if pairwise comparison says A is better than C, good. And between B and C, B better than C, then we have only one logical conclusion. A is better than B is better than C. That's the output of the voting system. Except sometimes we run into a problem, which we can easily identify right away. Maybe A is better than B. Okay, written with this arrow pointing from A to B. And B, pairwise comparison is better than C. And C, pairwise comparison is better than A. Then that will be a problem. Say, well, is it really that easy to generate such problematic situation? It's actually very easy. For example, I got 3 voters and 3 candidates. The first voter says A is better than B, B is better than C. Second voter says B is better than C, C is better than A. The third one says C is better than A is better than B. Alright, now let's do pairwise comparison between A, B. Well, A is better than B, B is better than A is better than B. So A is better than B, there are 2 votes. B is better than A, only 1 vote. So A is better than B wins. Alright, so we're just doing a majority count of the pairwise comparison. What about AC comparison? Well, A is better than C, but now C is better than A and C is better than A. So C is better than A receives 2 instead of 1 vote, and therefore C is better than A. Now at this point, just by transitivity requirement, you say we better have the following result. C is better than A is better than B. We really need C to be better than B. Otherwise, we'll be in trouble. Well, let's see. Let's compare B and C. And do we get C better than B? Well, B is better than C, B is better than C, C is better than A. B is better than C actually gets 2 votes. So B is better than C, not the other way around. And now we're in trouble. Because A is better than B, B is better than C, C is better than A. Each of the 3 input is transitive, yet the output is cyclic. This highlights the problem with so-called Condorcet voting, named after another French mathematician right after Borda, who further extended the rigorous study of voting systems. So pairwise comparison makes each comparison easy, but the overall voting output may be cyclic, as this simple example illustrates. So in the next video segment, we will look at another case where we see not only is Condorcet voting problematic, but all voting systems might have some problematic issues.